Hello everyone! This video illustrates our work presented this year at ICASSP' conference on learning a data efficient framework for real-world multiple sensors to localization, a work which was conducted at Agravante Research. After a brief introduction on sensors localization, I will show a deep learning-based solution to the task and motivate the need for a data efficient framework. Next, I will detail the two main contributions of the paper, which are first, improving the real-world performance with unsupervised domain adaptation, and second, learning layout invariance with an explicit transformation layer. And then I will go through the conclusion. The ability to localize the origin of sound is a natural gift to human beings, thanks to their 2 ears. In the exciting research topic of sensors localization, we are interested in transferring this ability to machines. This has numerous applications, including the monitoring of human activities in home environments, directly from the sound, enhancing human-robot interactions, and even in manufacturing. Now let's go through a more precise definition of the task and existing methods to solve it. Here we are concerned with the task of 2D multiple sensors localization, whereby the inputs are the extracted features from 2 or more microphones, and the output is the 2D XY coordinates in a horizontal plane of the sources. Classical approaches use phase difference between sound signals captured by microphones of the same array in order to infer the direction of arrival of the sound. By combining multiple directions of arrivals from different arrays, one can infer the XY position of the source. However, in the presence of multiple sound sources, an issue known as the association ambiguity problem rises. This issue is that there could be more candidates than actual sources. Data-driven approaches, and in particular deep learning-based method, can solve this issue by directly mapping sound features to locations. Another benefit of this method is that they can adapt to difficult acoustic conditions. Nevertheless, this method needs a lot of data to train, data which needs to be specific to the microphone configuration. In a previous work, we introduced a framework for this task. It consists in extracting and encoding features from different arrays independently and then decoding them together to obtain heat map representation from which we can refine the final location of the sources. As you can see, recording real-world label data from different microphone configuration is a very tedious task. This is why in this paper we are interested in a more data-efficient framework. The first thing we are interested with is to leverage synthetic training data. On the one hand, synthetic data is really easy to generate together with labels, but once we train a system on synthetic data, we observe a significant drop of performance when tested on real data. On the other hand, real data is very relevant for the downstream task because it shares similar acoustic conditions, but collecting real-world annotated data is very expensive. The solution is to close the gap between real and synthetic domains by using unlabeled real-world data. The second problem we wish to tackle is the generalization to microphone layout configurations. Indeed, if a model was trained on a fixed configuration, it will not be able to localize sources if we change this configuration. We propose a solution to enable localization without having to capture data for all possible layouts. First, let's see how we can improve the real-world performance with unsupervised domain adaptation. As we have seen right before, there is a domain gap in the sound space between the synthetic and the real-world data. One solution would be to expand the synthetic domain by either having a more realistic simulator or by randomizing the simulation parameters, such as to cover the real domain. Another solution which proved more successful was to reduce this gap in a feature space instead of the sound space by leveraging unlabeled real-world data. This is the method we will detail next. This can be done in 2 ways. In both cases, the model is trained with a task-specific loss, and a discriminator is introduced at an intermediate feature level in order to align the distribution of features from the different domains. In the first case, this is a traditional game framework, whereby 2 different objectives are used to update different parts of the models, which are the discriminator and the encoder. The second method uses a gradient reversal layers and is able to reduce the number of adversarial objectives to 1 and is also faster to train. This figure illustrates how this method can be applied in the case of sound source localization with either intermediate, output, or ensemble of discriminators. The ensemble learning approach resulted in the best performance by effectively closing the gap between intermediate features and heatmap outputs for both synthetic and real domains. Moreover, if we look at the numbers for two different datasets, we can see that we get a performance almost as good as if we had real labels, but our method only uses unlabeled real-world data. Next, we show how we can achieve layout invariance with an explicit transformation layer. As we have seen in the beginning of the talk, microphone arrays are good at estimating the direction of arrival of sources. The intuition behind our method is to extract features for each array in its own referential and then make the features compatible by using the known spatial transformation to go from one array to the other. These features are then processed by a few convolutional layers to obtain the final heat map of the sources. A naive solution will be to feed the relative pose between arrays to the model thanks to a fully connected layer. However, this is not very efficient because it will represent some extra parameters to be trained, and the model will have to learn implicitly how to take into account this transformation. Here is how the transformation layer is inserted into the model. The strength of our approach is that there are no learnable parameters, it is fully backpropagable and can be extended to more than two arrays. We simply apply the non-transformation to all feature channels by using grid sampling and interpolation. Here are some quantitative results. First, we can see that when we train on a single microphone configuration, only our method is able to generalize to new configurations. Moreover, when there are different microphone configurations in the training set, our method still outperforms the other baselines. To conclude, towards practical deep learning-based sound source localization systems, we reduce the burden of real-world data collection by closing the synthetic to real domain gap by unsupervised domain adaptation without using any real labels, and by using explicit transformation inside the deep neural network to learn layout invariance. Thank you very much for listening, and don't hesitate to reach out if you have any questions.